Yeah, hi students, very good evening everyone. Welcome once again to Om Institute and welcome once again to the IIT Guwahati PYQ series. Yes, so we are discussing this IIT Guwahati previous year questions, and IIT Guwahati previously conducted the GATE examination in 2010 and 2018. It's a 8-year cycle, you know, for the 8 organizing bodies. Okay, and next term 2026 is just a second. Yeah, yes, students. Okay, so 2026 has to be conducted by IIT Guwahati. Okay, and yeah, let's start discussing our questions. This is the control system part number 2. As you might be aware that on Monday we already had the control system part number 1. Good evening, Sai Vikas. Good evening, Akhila. This is the part number 2, and of course this part number 2 for control system brings on more important topics, okay, like the Bode plots, Nyquist plots, state space analysis. All those questions will be taken up today. This is the control system part number 2, as you might be aware that. Yeah, so audio video everything looks fine. Okay, any confusion or any problem with the audio video at your end, you can also let me know. Okay, fine. Yeah, so everything looks good. Let's get started. Let's get started and let's get moving ahead with the first question for the day. Yeah. Here it is, the first question for the day. For the asymptotic Bode magnitude plot shown, the system transfer function can be GATE 2010 EC 1 mark question. Okay, very simple question, calculating the transfer function from the Bode magnitude plot given. Okay, for the asymptotic Bode magnitude plot given, the transfer function. Okay, so basically what is mentioned, the two corner frequencies are mentioned. Okay, and this is a corner frequency 0.1 where the slope is increasing. Okay, so rather if I calculate the slope of the line, let's come up to this slide. Okay, first let me write down the slope of this line. By the time, meanwhile, you can also solve and write the answer for me. Okay, so what is the slope of this line? Okay, so you can check the change in the magnitude. Okay, the change in magnitude, okay, the change in magnitude is 40. Okay, 40 decibel from 0 to 40. Okay, from 0 to 40. But what is the change in the frequency? And remember, it has to be logarithm scale. Okay, so what is the change in frequency? 0.1 to 10 is like into 100. Okay, is into 100 means into 10 and into 10. It's like into 10 and into 10. Okay, that is 2 decade. A factor of 10 is 1 decade. So the slope is 40 decibel per 2 decade, and hence I can say that the slope is 20 decibel per decade. Clear enough? Okay, the slope is 20 decibel. Okay, so see, initial slope was 0. Okay, and then there comes a point where slope becomes plus 20. So this has to be the 0 corner frequency. And then at this point, the slope again becomes 0. The line parallel to x-axis, again slope is 0. So this has to be a pole corner frequency. Okay, this has to be a pole corner frequency. Now what about the initial part? Okay, what about the initial part formula, so that I can write down the final answer? Remember guys, one important formula always in Bode plot analysis. Okay, this inverse question actually, when given the Bode magnitude plot and you need to find out the transfer function. Okay, initial part, okay, I write down as the formula as minus 20n log omega plus 20 log k. Minus 20n log omega plus 20 log k. Minus 20n log omega plus 20 log k. Okay, I assume n poles at origin. If there are zeros at origin, that becomes plus 20n. Okay, in case of zeros at origin. Okay, so what I have assumed right now here is, n is the poles at origin. Poles at origin, and this also gives the very famous formula, initial slope minus 20n. Okay, but what about the initial slope? You can see from here. What is the initial slope? We can see from this particular plot is 0. So there are no poles at origin. N is equal to 0. So the initial magnitude here, so the initial magnitude should only be written as 20 log k, and that also is 0. What is the initial magnitude? You see here, na? Initial magnitude 0. It's on the x-axis. So dear, if you write initial magnitude as 0, that means 20 log k is 0, and hence scale, because log 1 is 0, so k equal to 1. Okay, k equal to 1. Okay, so we know that the constant multiplier is 1. Okay, there is one simple pole, there is one simple 0. Okay, so what is going to be the transfer function? What is going to be the transfer function? Let me write down that transfer function. So I can write down the transfer function as the k factor, which is 1. Okay, pole term 1 plus st. Now what is the time constant? Time constant is reciprocal of the corner frequency, because corner frequency is 1 upon time constant for the simple pole, or say for the first order pole or first order 0 term. Okay, so for the 0, the corner frequency is 0.1. Okay, so what is the time constant? Okay, 1 upon 0.1. For the pole, now look into the pole, the corner frequency is 10. Okay, so the time constant 1 by 10. Okay, and hence your answer must be s upon 0.1 is 10s. 10s plus 1 upon s by 10, that is 0.1s plus 1. Correct. And hence, going back to the option, okay, option number A perfectly matches our discussion. 10s plus 1 upon 0.1s plus 1. Okay. Option number A. Okay, dear. Option number A is all correct option here. Okay. Okay, now, very simply, that I have explained you in detail. Very simply now, if you just have to match the option, okay, if you have to match the option, this corresponds to the term, okay, this is a 0 term, as I explained you, this is a 0 term. So, because slope is increasing, slope increases to plus 20. So, 0 term will come in the numerator, 1 plus st, 1 plus s upon 0.1, that is 1 plus 10s. Okay, then corresponding to this is a pole term. Okay, pole term we know goes to the denominator, so 1 upon 1 plus st, 1 upon 1 by s plus 10. Okay, that is 1 upon 0.1s. Combining these two itself, option number A. I mean, if you have to very quickly come to the answer, yeah, 0.1, option number A by this basic calculation. Clear enough? Okay, if this is clear enough, let us be ready for the next question. Coming up straight here it is. The asymptotic Bode magnitude plot of a lead network, okay, it's on lead compensator actually, okay, with its pole and 0 on the left half of the S plane, pole and 0 both on the left half, that means they have taken minimum phase case only. The frequency at which the phase angle of the network is maximum. Okay, from the Bode you should directly know the result. Okay, the frequency, okay, at which the phase angle is maximum is given by what? Okay, normally you can write down the lead network transfer function as 1 plus st1 divided by 1 plus st2. Let me write it even more clearly. Okay, you can write down that lead transfer function as 1 plus st1 divided by 1 plus st2. Okay, lead means 0 dominant. 0 should be closer to the origin. Okay, but then what is the frequency? Okay, at which the maximum phase angle occurs. From the Bode plot directly you should know, otherwise from the given Bode plot first you will write down the transfer function and then you will use the formula. Okay, then you will use the formula 1 upon under root t1 t2. Okay, but 1 upon t1, 1 upon time constant is corner frequency, we just revised. So 1 upon t1 is first corner frequency, 1 upon t2 is second corner frequency, and we can write this as under root of omega c1 omega c2. Dear, you can write this as under root of omega c1 omega c2. Clear? Okay, omega m, the phase, the frequency at which maximum phase lead occurs is the geometric mean of the corner frequencies of the pole term and the 0 term. I repeat, it is the geometric mean of the corner frequency of the pole term and the 0 term. Okay, so what is that calculation? Okay, so hence calculation is under root of 0.1 into 0.5. Options are in the numerator but denominator fractional form. So I can write this as 1 upon 0.1 can be written as 1 by 10, 0.5 is 5 by 10. Okay, so 5 by 100 or 1 by 20. So under root 1 by 20. Option number B. Finished. Option number B it is. option number B it is. Okay, tell me for any confusion if you have. Option number B is the correct option. 1 by root 20. Okay, fine dear. 1 by root 20. Okay, option number A, B correct. Correct, Sai Vikas. Option number B now. Next question. Be ready for the next question. The approximate gate instrumentation. Okay, so the previous one was that also was instrumentation 2 mark, gate 10. This is gate 2018 instrumentation. As I told you, for common subject, I will consider all the three branches, EC, EE and IN. All three questions are being discussed. So gate 2018 IN 1 mark question. Gate 2018 IN 1 mark question. Thank you, Gokul. Great to know that. Great and good that you are learning, you are enjoying. Keep excelling in your life. Okay, keep chasing your dreams, work hard. Okay, now the approximate phase response. The approximate phase response. See, for a simple understanding of this one, okay, you can just break this into two parts. 100 square. So see, 100 square, let me call it as omega n square upon s square plus 2 zeta omega ns plus omega n square, again 100 square, into the transportation lag term e power minus st term, e power minus 0.01 s. Okay. Now what is the, see, the question is very clearly, if you read the question, approximation to be done by Bode. Okay. See, if you see the option number B is what is known as the approximate phase plot. Okay. For omega n square, only for omega n square upon s square plus 2 zeta omega ns plus omega n square. Okay. Now see, at some places you have to use your direct notes and conclusion. You don't have to derive the phase response, at least for the first order pole or 0, for the second order pole term. These are standard, very standard results, okay, of the Bode plots. Okay. So if it is only omega n square upon s square plus 2 zeta omega ns plus omega n square, a standard second order transfer function, option number B is the phase response. Now multiplied by a transportation lag. Multiplied by a transportation lag. So what is the role of this transportation lag? Okay. What is going to be the phase of this part? Okay. With respect to phase, okay, I can say that the phase of this part, e power j theta, the phase will be theta. Okay. So that is going to be minus 0.01 omega. When you convert s to j omega, s equal to j omega, convert to the frequency domain. Okay. Minus 0.01 omega. And what is the corner frequency? Let me also tell you that corresponding, okay, to the second order transfer function, okay, this change in phase, the phase is approximately taken as 0 up to the corner frequency. Okay, up to the corner frequency, and the phase is minus 180. Okay, this is omega greater than omega n and this is omega less than omega n. The phase is approximated by 0 for frequency greater than the corner frequency. Corner frequency here is equal to omega n only. Okay, omega n. Omega n is 100, as you can see. Okay, but now because of that additional, okay, transportation lag term minus 0.01, it's like y equal to mx. It's like y equal to mx, a straight line of negative slope. Okay, so before this part, which was constant 0, there will be a straight line of negative slope. Okay, at 100 it will be having some phase that you can convert to degree, because if you see the phase is in degree and this particular phase of course is in radian, you can convert to degree. Okay, but not required to calculate actually. At omega equal to 100, you can substitute 100, there will be some phase coming up that you can convert to the degree, not required. You can see the nature, there will be a straight line portion, then the sudden change in the phase, and then another straight line of negative slope. Okay, that itself suggests that option number A. That is clearly suggesting option number A. That is clearly suggesting option number A. Okay, because this brings up, okay, the phase, I'll write down here also, minus 0.01 omega, and that is like y equal to mx. Okay. Okay, Gokul, you can search the telegram by my name, or I will share you the link. Just wait, I'll share you the link as well. Okay. Correct, guys, option number A. Right. So I'll say this is a simple but little bit different question. Okay. Now GATE 2018 IN 1 mark question. Again GATE 2018 instrumentation 1 mark question on the phase margin. The phase margin in degrees. So, okay, so consider this transfer function. What is the phase margin in degrees? What is the phase margin of GS in degrees? Okay, GS is 2 upon S plus 1 S plus 2. What is the phase margin in degrees? For the phase margin, first of all, what we need is the gain crossover frequency, correct? Na? What we need is the gain crossover frequency. Let us calculate that gain crossover frequency. Okay, let us calculate. First, let's convert this function into the frequency domain. Okay, so what is there? Gj omega, okay, is 2 upon 1 plus S. So that becomes 1 plus j omega into 2 plus S. That becomes 2 plus j omega, correct? That becomes 2 plus j omega. Okay, now if I first start calculating the magnitude mod gj omega, okay, so that will become 2 upon magnitude of complex term root over x square plus y square, the root over 1 plus omega square root over 2 square plus omega square, correct? Now phase margin is calculated at omega g, and what is omega g? Gain crossover frequency, the frequency at which the magnitude is 1. Okay, the polar plot, with respect to polar plot, you say polar plot crossing the unit circle. Okay, polar plot crossing the unit circle. Okay, so at the gain crossover frequency at omega equal to omega g, magnitude is 1, and magnitude, which I have just now written as 2 upon under root of 1 plus omega square 4 plus omega square, both of them take under root, this should be equal to 1. Okay, so squaring and simplifying, squaring this 4 and right side under root will cancel, 1 plus omega square 4 plus omega square I have squared, and to solve it you can simply assume, okay, you can simply assume omega square equal to x. Okay, if you put omega square equal to x, so you will have the relation 4 equal to x plus 1, omega square plus 1, omega square plus 4. So x plus 1, x plus 4, which is x square plus 4 plus 1, 5x plus 4. Right, 4 cancel, x square plus 5x equal to 0. But this will give you two possibilities. X, remember that x is omega square. This will give you the solution as 0 or minus 5, but the square, okay, the square cannot be negative. Omega, the frequency is a real term, the square cannot be negative. Okay, so the only possibility for omega is 0. Okay, omega g, the gain crossover frequency is 0. Then what is the phase margin formula? Then what is the phase margin? It is straight formula question only. Then dear, what is going to be the phase margin formula? The phase margin is then further given by 180 degree plus angle gj omega g, phase at omega g, 180 degree plus what is the phase? Now phase of this function, okay, phase of this function, numerator is positive real number, denominator tan inverse omega, denominator we subtract the phase, so minus tan inverse omega g, and then the next is 2 plus j omega, so tan inverse omega by 2, omega g by 2. But dear, omega g is 0, so tan inverse 0 is 0. Okay, so answer is 180 degree. The NAT question, yes Sai, because correct answer 180 degree. 180 degree. It's a NAT question, I can enter 180 degree here. It's a NAT question, I can enter the 180 degree here, correct? Okay, yeah, next question. Let's be then ready for the next question. Just a second, is this some glitch coming up or what? Just a second here. Yeah, so this one is done. Yeah, next question. GATE 2018 EC 2 marks. Okay, good question. Okay, it's a good question. Let's read this. The figure below shows the Bode magnitude and phase plots of a stable transfer function GS. Okay, this is the Bode plot for stable transfer function GS. Okay, n naught upon SQ plus D2S square plus D1S plus D naught. Consider the negative unity feedback configuration. consider the negative feedback, unity feedback configuration with the gain k in the feed forward path. So GS is cascaded with k in the feed forward path. Okay, and it's a unity negative feedback system. The closed loop system is stable for k less than k naught. What is the maximum value of k naught? Okay, what is the maximum value of k naught? See, if I talk about the stability of the original system, original closed loop system without k, GS is stable. GS means open loop gain is system. But what about without k? Okay, see, if you take without k, okay, without k, what is your block diagram? When I say without k, that means I am talking about this picture. When I only take GS and connected in the unity negative feedback. Okay, is the system stable or not? Okay, so the Bode magnitude and phase plot is given. Dear, the Bode magnitude and phase plot is given to you. Okay, from the magnitude or phase plot, any one point, okay, that you can pick up, any one important point, look into this point. Okay, look into this point. This is the point where the phase is minus 180 dear, and the frequency dear at which the phase is minus 180 degree is known as what frequency? Okay, this frequency not mentioned, but this frequency is omega p, phase crossover frequency. We know that where the phase is minus 180 degree, the frequency is known as the phase crossover frequency. Okay, the frequency is known as phase crossover frequency. Okay, so hence correspondingly, if I go, same line has been mapped to the above plot, so we know the omega p. And then what is calculated at omega p? Gain margin. What is calculated at omega p? Gain margin. Okay, what is the magnitude of the system? Now, dear, from the Bode plot, okay, from the Bode plot, what is the gain margin? Okay, let me write down this formula here, just a second, I'll move aside. Okay, from the Bode plot, what is the magnitude? What is the gain margin? It is negative of, because see, what is the gain margin general formula? Forget from the Bode plot. See, how do you write down the gain margin formula actually? The gain margin is given by 20 log 1 upon magnitude unity feedback, correct? And then I can write this as minus 20 log 1 by x is minus log x, na? Minus 20 log mod gj omega p. Okay, then what you should know that although they have written this as mod gj omega, but in Bode plot, okay, this magnitude is actually 20 log mod gj omega. 20 log mod gj omega. So at omega p, what is the magnitude in decibel? At omega p, it is 20 decibel. Okay, so the gain margin is minus 20 decibel. Negative gain margin, unstable system. Okay, although GS may be stable, but the closed loop system is unstable. Is that clear to everybody? The closed loop system is unstable. The closed loop system is unstable. Okay, the closed loop system is unstable without K. I have explained you the problem without K. For that reason, now what they have done is, okay, now they have, okay, connected, okay, the system with the gain K in the feed forward path. Okay, and then they say the closed loop system is now stable for some value of K less than K naught. What is that value of K naught? Maximum value of K naught. Okay. Warrior, the institute number is 9515694053951569405394053. 951569405394053. Okay. Yeah. So now come to this system, okay, where the gain K has been connected in the feed forward path. Okay, so what is there in the frequency domain? We can write down the open loop gain as kgj omega, kgj omega. Okay, let this be the new open loop gain g1j omega, kgj omega. But dear, K, okay, K is a real number, so it's not going to affect the phase. If you talk about angle g1j omega will be equal to, the angle of K is not there, it's 0 for the real number, positive real number, angle gj omega. So because the angle expression has to be same, so what can you say? Okay, there has to be same omega p, phase crossover frequency. Okay, the phase plot will remain to be same. Okay, the same omega p, because omega p depends on the phase. Omega p is the frequency at which phase is 180 or minus 180. Okay, so no change in phase expression, same omega p. Okay, but what about the magnitude? Okay, now if you write down 20 log mod of g1 j omega for the new system, 20 log mod of g j omega will be equal to 20 log of mod of how much? K g j omega. Log of a into b, log a plus log b. Log of a into b, log a plus log b. 20 log g j omega. Now dear, tell me what is the gain margin? Gain margin is minus 20 for the new system. As I just explained you, gain margin is minus 20 log mod g j omega p, 20 log mod of g1 j omega p, g1 j omega p, and that will be equal to, now taking the from the previous expression, let me again move aside, minus 20 log k and minus 20 log mod of g j omega p. Okay, and from the original system, what is 20 log mod g j omega p? This value is 20, as I already explained you. So the gain margin is now equal to minus 20 log omega minus 20. Okay, minus 20 log omega minus 20. Hope that is clear. Minus 20 log omega minus 20. Okay. So dear, what I have obtained, that the gain margin is minus 20 log omega minus 20, but you need the condition for stability. Okay, the system is stable if the gain margin is greater than 0 dB. In terms of decibel, it has to be positive. In terms of decibel, it has to be positive. Okay, so this minus 20 log k minus 20 is positive, or you can say that 20 log k is less than minus 20. Okay, or 20, if you cancel, log k is less than minus 1, k is less than, taking the exponent 10 power minus 1, so k is less than 0.1. Okay, k is less than 0.1, hence the value of k naught is 0.1. Good question. Stability and Bode plot analysis. 0.1. Okay. So that is why it's always important to solve even especially good PYQ, so that you learn. Okay, you learn, more and more variety of concepts. Okay, answer is 0.1. Answer is equal to the 0.1. Okay, answer is 0.1. Okay. Yeah. Then let's go to the next question. Okay, GATE 2018 IN 2 marks question. Fundamental question on the understanding of the Nyquist stability formula. Okay, consider the standard negative feedback configuration with GS equal to, given GS is S square plus 0.2S plus 100 upon S square minus 0.2S plus 100, and HS is equal to 1 by 2. Feedback gain is given. The question is the number of clockwise encirclements of minus 1 comma 0 in the Nyquist plot. Okay, the number of clockwise encirclements N is, we know, given by formula P minus Z, P plus minus Z plus. Since they mentioned clockwise encirclement, okay, so of course, assuming the clockwise Nyquist contour, for the clockwise Nyquist path, we take the formula P minus Z, correct? Okay, so understand by this formula, N is equal to the P minus Z. N is equal to the P minus Z. Okay, P plus minus Z plus, I am being more specific. Okay, so that plus means the right half zone. Okay, so the number of encirclements given by this formula. Now, what is P plus and Z plus? Okay, a quick revision. Okay, what is P plus and Z plus? P plus, number of open loop poles. Okay, that is number of poles of GSHS. Number of poles of GSHS in RHP. Plus means right side zone. What is Z plus? Z plus is known as the number of zeros of, because you talk about the encirclement of shifted origin, we have the number of zeros of 1 plus GSHS, okay, in RHP, and the number of zeros of 1 plus GSHS. Okay, zeros of 1 plus GSHS also mean the roots of characteristic equation. The roots of characteristic equation, correct na? Okay, roots of characteristic equation. So let's solve it now. Everything is given. It's not on drawing the Nyquist plot. It's not that you start drawing the Nyquist plot of GSHS and then see how many encirclements. That will become lengthy. Okay, just by using the stability formula, Nyquist formula, you can get the answer. You can get the answer, correct? Okay, just a second here, I think. Yeah, complete this. I have given you the hint. Just a second here, what has happened? I need to check it. Hello, 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 hello. Yeah, it must be audible now. It must be audible now. Okay. Yeah. So nothing, guys. Even if it was not audible, I don't know from which point the audio went, but I've just calculated the poles. Simple quadratic equation formula. Okay. And I've got both the poles in the RHP. Okay. Hope this part is clear. Both the poles are in RHP. Now, the next thing that you need is, okay, let me go back. Yeah. The next thing that you need is Z plus, which is the number of roots of characteristic equation, zeros of 1 plus GSHS. Okay. So what is that characteristic equation? Let me solve that. Let me frame that characteristic equation separately. Okay. 1 plus GSHS, GS 1 plus 0.2 S plus 100 upon S square minus 0.2 S plus 100 into HS is 1 by 2, and this has to be equated to 0. Okay, so solving this, see, I will have 2S square. Okay, then 2 into 0.2 minus 0.4s plus 2 into 100, 200 plus, then what will you get? S square plus 0.2s plus 100 equal to 0. Solving it dear, 2 plus 1 3s square minus 0.2s plus 300 equal to 0. And once again, if you solve for the roots here, s will be equal to minus b, which is going to be plus 0.2 plus minus root over b square 0.2 square again 0.04 minus 4ac, 4ac, 4 into 3 12, 12 into 3 3600, but again 0.04 minus 3600 negative, and under root of negative number imaginary root divided by 2a. So this is again going to be 0.2 by 2 cancel, 0.1 by 3 plus or minus j something. Okay, so both are in RHP. Okay, 2 RHP, z plus is also 2. Now dear, if z plus is equal to 2, I'll write down the answer here. N is p plus minus z plus. Okay, p plus also calculated 2, z plus also calculated 2, answer is 0. Answer is equal to 0. Okay, take down, understand the calculation, simple it is. Okay, answer is 0. Okay, let me go back and enter the answer. What is the answer to the question? Is 0. Okay, fine. Okay dear, then let's go to the next question, of course. Okay, GATE 2000 EC 2 marks. Okay, there used to be common data questions, okay, till the paper was offline. Okay, so there are common data questions. Okay, the signal flow graph is given and there are two questions. The number one is state variable representation and number second question is going to be the transfer function. So you can calculate the transfer function from state space model also, but you can calculate transfer function directly from Mason's gain formula. Graph is given, na? Okay, graph is given. Okay, so what is the state variable representation of the system? What is the state variable representation of the system? Okay, yeah, thanks Bhargav, keep putting your efforts, keep learning. Okay, so now state variable representation. So normally when I have to derive the state space model from the given signal flow graph, okay, we assign the output of every integrator. Now what is integrator? Every 1 upon s represents an integrator term. We know that 1 upon s, okay, is the integrator transfer function. 1 upon s is the integrator transfer function. Output of every integrator is a state model, is a state variable. Okay, as a normal convention, it's a convention, it's not a theorem or rule. Okay, so normally if you follow the convention, okay, that the state variables are assigned from right to left. Okay, so if I go from right to left, now this is 1 by s, this is my first integrator and I will name this output as state variable x1. Let this be state variable x2, and then you go towards left, right to left, this is another integrator, okay, and this output will be x2. But at the same time dear, 1 upon s is an integrator. If the output of an integrator is x1, what can be the input? What can be the input? Okay, so suppose you understand this way. Okay, suppose you apply input xt, you obtain the output yt, and suppose this is an integrator system where yt is written as integral x tau d tau, correct? Integral minus infinity to x tau d tau. But as per the Laplace property, okay, we can write down ys as integral x tau d tau, Laplace is xs by s, and hence the transfer function of the integrator, okay, the transfer function ratio of output by input in the s domain is 1 by s. So that's why I told you 1 by s is the integrator block. Okay, but then what is the next point? If the output of the integrator is is suppose some variable x, if the output is x, what should be the input? Think reverse. What should be the input? Okay, input can be taken as derivative of x because the integral of differential will cancel and then you get x. Okay, so what should be here? Okay, what should be here? The derivative. Okay, what should be here? D by dt of x. Okay, when you integrate a differential term, the integral differential cancel, answer will be equal to x. The answer will be equal to the x. The answer will be equal to x. Correct? Okay. So if the output is taken as x, input can be taken as derivative of x or derivative of x, which we will write as x dot. Okay. So now come back here. So if dear this is x1, the output of this integrator is x1, the input here, okay, can be x1 dot, but at the same time it is also x2. Okay, and here if the output is second integrator is x2, we'll take the input as x2 dot. Okay, and now we'll start writing the equation. Okay, options are only considering the equation of this state variable, the state space equation. Okay, not the no, even output equation is given. Okay, yeah, the complete state space equations will be there. Complete state space equations will be there. Now see, what is x1 dot? Very carefully read with me and try to write down the answer. What is x1 dot? What is x1 dot? Now x1 dot, okay, is also equal to x2. It is colliding with x2 also, but at the same time at x1 dot there is one more incoming line. Everybody see carefully, at x1 dot there is one more incoming line, and that incoming line is from x1 multiplied by this gain minus 1. This gain minus 1. So minus of x1. Then we will rearrange. Okay. What is x2 dot? What is x2 dot? This is x2 dot. Okay, so it has an incoming line from input, that is 2 into input, and also one more incoming line, minus 1 coming from x1. Minus 1 coming from x1. So we'll write it as minus x1. Okay. What about the output, dear? Okay. What about the output? Let me write down the output for you here itself. Just a second. Yeah, let me write down the output for you here itself. Output is 0.5 times what? 0.5 times whatever the value at this node. So what is the value at this node? See, 1 into, this is x2, 1 into x2 and also 1 into x1. Okay, so this node is x2 plus x1. The output is 0.5 x2 plus x1. Now rearranging, just rearranging there. Let me write down these equations when rearranged. Okay. The equations when rearranged. Okay, so what is the first equation? x1 dot, okay, is minus x1 plus x2. We got x2 minus x1, writing it as in the sequence form, x1, x2 and the input term. Minus x2 plus x1 plus no input term here, 0 into u. What is x2 dot? The x2 dot equation is 2u minus x1. So writing it as minus x1. There is no x2 term, 0 into x2 plus twice of the input term. Okay, and the output is 0.5 x2 plus x1, or I can write this as 0.5 x1 plus 0.5 x2. Now you can see what the matrix A will be. Okay, in the matrix form, x dot will be, now in the first equation, what is the coefficient of x1, x2? Minus 1 and 1. In the second equation, x2, x1, okay, sorry, this was minus of x2, sorry, this was minus of x1. This was minus of x1, correcting it here. Okay, so x1 coefficient minus 1, x2 coefficient 0. Okay, into x plus how much input? 0 and 2. First equation 0, second equation 2, plus 0 to u, and y is equal to, okay, cx. Okay, x1 coefficient 0.5, x2 coefficient 0.5. This is the state variable representation. This is the state variable representation to be matched with, okay, what I have got, minus 1, 1, minus 1, 0, minus 1, 1, minus 1, 0. Option number D, output 0.5, 0.5, option number D. Option number D, correct? Akhila, correct answer, D. Correct answer, it is D. Okay, tell me for any doubts. Okay, and as I told you, it is a common data question containing of two questions. Okay, the second question is directly the transfer function. Okay, and you know, the second question is directly the transfer function, which you can solve directly by MGF, Mason's gain formula. Okay, so the questions, you know, by a fundamental question on Mason's gain formula, you solve it on your own. Okay, this is a homework for you. This is a homework for you. Let's go towards more question of state space analysis. Okay, so hope you can complete this. Hope you can complete this. Okay. So complete this is a Mason's gain formula. Okay, we can find a transfer function from state space model also, but finding it from MGF since the graph is given. Okay, because there are some questions. Now have a look into this next question. Gate 18 EC 2 marks question where signal flow graph not given, directly the state variable representation of a system given, you have to find a transfer function. You have to find a transfer function. You have to find a transfer function from the state variable representation. You have to find a transfer function. Okay. Come on, let's do this. Okay, yes Kavita, correct answer for the previous one, that is D. Okay. Okay, what is the transfer function of the system from the state variable representation? From the state variable representation. See now, first observation for this question, especially for this question, the first observation, all denominators are same. Okay, all denominators are same. If you look into all the four options, all denominators are same. Denominator same means same characteristic equation. Okay, so if I observe here, all options same denominator, that means same characteristic equation will be formed. Okay, so I'll use a simple principle. Okay, I'll just copy these equations first. I only need the matrix A. Okay, so dear, what is the simple principle I am going to use? Characteristic equation of system, okay, is simply equal to the characteristic equation of the matrix A, and hence, okay, what is the characteristic equation of matrix A? Matrix A is 2 cross 2. Okay, 2 cross 2 characteristic equation. Apply the fundamentals of linear algebra. Okay, for a 2 cross 2 matrix, what is the direct characteristic equation? You can write lambda square minus trace into lambda plus determinant equal to 0. Okay, so lambda square minus trace means sum of diagonal elements, minus 4 plus 0 plus determinant, okay, into lambda plus determinant cross multiplies 0 minus of 4 into 1.6, minus becomes plus, also 4 into 1.5 is 6. Okay, so what is this? Minus here also plus lambda square plus 4 lambda plus 6 equal to 0. Okay, but now you see all options have the same characteristic equation. Now what I am trying to suggest to you, if there are options containing different characteristic equation, okay, this is what is the approach you can follow. Now what is the characteristic equation of the system then? Okay, we write down the characteristic equation of system in S domain as a S variable, S square plus 4S plus 6 equal to 0, and hence all options have S square plus 4S plus 6 equal to 0. Okay, so see, this is one approach I have told you in case options have different characteristic equation, correct? But now all options have same characteristic equation, so just this which will not happen. So how do you find a transfer function? Again, transfer function, before you apply the formula of transfer function, you see if there is any standard form. This is not in any of the standard form, okay, but if the transfer function is in standard form like CCF, OCF, DCF and GCF, these 4 standard forms you study: controllable canonical form, observable canonical form, the Jordan canonical form, diagonal canonical form, then you can directly write the transfer function by the knowledge of those models. Here it is none of the standard form. General expression for transfer function, is given by, okay, C phi B plus D. Okay, where ABCD matrices, you know what is phi S? Phi S is known as the Laplace transform of the state transition matrix phi T, and phi S is given by what formula? It is given by the formula SI minus a whole inverse. Okay, what is phi T? Dear, phi T, a quick revision, phi T is known as, it is an important thing, state transition matrix. Phi T, state transition matrix, basically defined by e power at. And that is why we see, if you have to calculate actually phi T, okay, so phi T becomes the inverse Laplace. If phi S is the Laplace of phi T is the inverse Laplace of phi S, that is the inverse Laplace of SI minus a whole inverse. Okay, here I don't have to calculate inverse Laplace, but just telling you the formula. Okay, Sai Vikas is ready with some answer, that is A. Okay, let's check out the correct answer then. Okay, so I need phi S. Okay, that is SI minus a whole inverse. So let's do some calculations around this question now. Okay, so what is SI minus a? First this much, then only inverse of the matrix will be calculated. So S into I becomes S0 0S, S into identity matrix minus A matrix. The A matrix is minus 4 minus 1.5 and 4 and 0 and 4 and 0, correct? So when I subtract these two, S minus minus 4, S plus 4, 0 minus minus 1.5 is 1.5, 0 minus 4 and S minus 0. Okay. Okay, this is Si minus A. Now, what is Si minus A whole inverse? I mean the inverse of this matrix, and we know that inverse of any matrix is given by what formula? It is given by the formula adjoint of the matrix divided by the determinant of the matrix. And adjoint of 2 cross 2 matrix is simple. What is the adjoint of 2 cross 2 matrix? Number 1 rule, exchange the diagonal numbers. Exchange the diagonal numbers, S plus 4. And off diagonal numbers, don't exchange but just change the sign. Minus of 1.5 plus of 4. For 2 cross 2, remember this is very frequent 2 cross 2 question on state transition matrices. Okay, so for diagonal numbers, exchange the diagonal numbers. For off diagonal number, don't exchange them but just change the sign. Plus 2 minus, minus 2 plus. Okay, plus 2 minus, minus 2 plus. Okay, Sai Vikas, remind me once. Okay, divided by the determinant. Okay, determinant of the matrix, cross multiply S plus 4 minus of minus plus 6. Okay, so this is Si minus A whole inverse. This is the phi s term. Okay, denominator can further be simplified. This becomes S square plus 4s plus 6. Now, what is the transfer function? C phi b plus d. Okay, now C phi b plus d. D is not given in the question, 0. Okay, okay, this is the A matrix. This is the B matrix, this is the C matrix, correct? So there is no D matrix. Okay, I will substitute at least the B and C what is required. Okay, so the next step is as I told you, the transfer function being equal to the transfer function, just a second, yeah, all okay, transfer function C phi B plus D. Okay, as I already mentioned, D is 0. Okay, but what is C? C is 1.5, 0.625. okay dear, multiplied by the phi matrix. What is the phi matrix just now obtained? S minus 1.5, this is S plus 4 and this is 4 whole divided by the denominator S square plus 4s plus 6 into the B matrix. And what is the B matrix? 2 and 0. Now dear, there comes a question while solving. What do you solve first, C into phi or phi into B? Actually you can solve any one first actually, but you should decide based on the numbers given. You should decide actually based on the numbers given to you. Okay, now as per the numbers given, I will prefer multiplying phi with B here. Why I will prefer multiplying phi with B? Because B has a 0 entry and 0 into anything is 0. So numbers will become small in the beginning. Otherwise you keep on taking the lengthy calculation till the end. Okay, so for that reason I will choose phi into B here. For that reason I will choose phi into B here. Clear? Okay, so if I multiply phi into B, this particular denominator will keep it outside only. Okay, so 1.5, 0.625, C is as it is. I am multiplying phi with B. Okay, so see, 2 into S, first row in column, S into 2 minus 1.50, so only S into 2. Then 4 into 2, 8 plus 0 into S plus 4, so only 8. So see, I told you na, if you multiply phi in B, you get a simpler result in the beginning, and that is important. Okay, whole divided by the same denominator, S square plus 4s plus 6. Now your answer is ready. Multiply this, one row and one column is given. 1.5 into 2, 3s plus 0.625 into 8, 5 divided by S square plus 4s plus 6. Finish. What is there? 3s plus 5 upon S square plus 4s plus 6. 3s plus 5 upon S square plus 4s plus 6. A, correct answer. Yes, I because also mentioned A, correct. Yes, A is the very correct answer. 3s plus 5 upon S square plus 4s plus 6. Done. 3s plus 5 upon S square plus 4s plus 6. Okay. Yes, Akila, correct. A answer. Okay. This is the complete method. Okay. But yeah, if you only wanted the characteristic equation, see here also characteristic equation, denominator comes up na, S square plus 4s plus 6. Okay, that can alone be solved if you only want the characteristic equation. If you only want the characteristic equation. Okay, I mean if the options have different characteristic equation, then this is a simple approach, but this question has different denominators, same denominators, so I have to solve the process completely. That too, the system given is none of the standard form. Okay, this is not in any standard form. Okay, this state space model is not in any standard form. This is not in any standard model. What are the standard models? CCF, OCF, DCF, JCF. You should always be aware about these four models, very important in the state space analysis. Okay, the standard models, the canonical models. Okay. Next question. Okay. Given the system x dot equal to ax plus bu and a equal to -1, 2, 0, 2, okay, b equal to 0, 1, the system is stable or controllable. The question is talking about stability, controllability. A is a upper triangular matrix. Okay, A is a upper triangular matrix. So stability part solved here only. Upper triangular matrix. Okay, so what are the eigenvalues? It's a upper triangular matrix, so eigenvalues are diagonal numbers. For any upper or lower triangular or diagonal matrix, eigenvalues are equal to diagonal numbers. So the eigenvalues are -1 and 2, and then the poles are corresponding to the eigenvalues, and the poles of a control system is the eigenvalues of matrix A. Okay, so the poles are -1 and 2, -1 and 2 plus 2, RHP. RHP pole leads to unstable system. There is a RHP pole, so the system is unstable for sure. Okay, controllability. Kalman's test. You cannot apply Gilbert's test. See, if it is an upper triangular matrix having repeated eigenvalue, upper triangular matrix but with non-repeated eigenvalues. Dear, if it is having repeated eigenvalues in upper triangular matrix, then it is Jordan canonical form. And DCF, diagonal canonical form, is diagonal matrix with non-repeated value. Okay, so the given model is neither DCF, that is very sure, okay, nor JCF. So you cannot apply the very simple Gilbert's test. Gilbert's test is only for DCF, JCF. So for controllability, you have to apply the Kalman's test. You have to apply the Kalman's test. Kalman's controllability test. Okay, you have to apply the Kalman's controllability test. Done, dear? Let's apply it. Okay, so what is the controllability matrix? Kalman's controllability matrix, okay, is given by S, which is augmentation of the matrices, which is B, AB, etc. up to A power n minus 1 into B. But our given matrix is of second order. So what is the S matrix? Is simply B, and A power n minus 1 is A power 1 only. Okay, so B and AB, only these two parts I need. B is given, we just have to multiply AB. Okay, let's multiply AB. Okay, A matrix -1, 2, 0, 2. B matrix 0, 1. Okay, this is 2 and then 0 and 2, this is 2. So 2, 2, multiplying the row and column wise. Okay, so what is going to be S matrix now? B matrix, which is 0, 1, AB matrix, which is 2, 2. Now check the determinant of S, 0 minus 2, non-zero. And if the determinant of the controllability matrix is non-zero, then the system is yes controllable. Then the system is controllable. So it is not stable but controllable. Option number C. It is not stable but controllable. Yes, Sai Vikas, correct answer. Sai Vikas, correct answer. It is not stable but controllable. Okay, not stable but controllable. Yes, Akhila, correct answer. No, sorry, Akhila has told D. No, just recheck it. It is controllable only, Akhila. Okay. Okay, next question. Gate 18, doubly 2 marks. Consider a system governed by the following equations. D by dt of x1 is x2 minus x1. D by dt of x2 is x1 minus x2. The initial conditions are such that x1 0 less than x2 0 less than infinity. Let x1f is t tending to infinity x1t and x2f is t tending to infinity x2t. That is the final values of x1 and x2. Which of the following is true? Which of the following is true? It's a good question. Okay, see. First of all, okay, let me write down this equation as x1 dot derivative is minus x1 plus x2, rearranging, and the second equation derivative of x2 dot is x1 minus x2. Okay, so if I have to write it in the matrix form, where is the input term? There is no input term given. Why? See, if you write this in the matrix form, x dot is equal to ax. Okay, what is the A matrix? First row minus 1 1. Okay, x1 x2 coefficient. Second row x1 minus x2, so 1 and minus 1. Okay, x dot equal to ax plus, that's it, x dot equal to ax. Okay, normally we write x dot equal to ax plus bu. X dot we normally write as ax plus bu. Okay, so there is no input term given. Okay, no input term. Okay, that means the input has been assumed as 0. Okay, input has been assumed as 0, and whenever you assume the input 0, what you calculate is ZIR, 0 input response. Okay, the question is talking about the final value of x1t and x2t. X1 and x2 we know are the state variables. Okay, so we have to first calculate x ZIRT. Okay, the state vector. Okay. Yeah, we know now what is that state vector. What is the state vector? It is nothing but a vector, a column vector containing both the state variables x1 and x2. What is xZIRT? What is xZIRT? Now, what is the ZIR formula? What is the ZIR formula? In time domain and S domain, both I will write. xZIRT is given by the formula phi t into x0, where x0 is the initial condition, where x0 is the initial state. Okay, what is the initial? What is some information on the initial condition? x1 0 less than x2 0 less than infinity. Okay, so if I have to define the initial state vector, see, I'll write down here. What is the initial state vector? Okay, I'll call it as x0, and that is known as x1 0, x2 0. To make the numbers simple, I'll write it this way. Suppose this is A and B, but what is given? A less than B, both of them are finite, both are less than infinity. A less than B, okay, further less than infinity. This much is the data given to me. This much is the data given to me, correct? Right? Okay, now, yeah. So coming up here, okay. See. So what is xZIRT? Phi t into x0. Phi t is not given, or if you take it in the S domain, x ZIRS, Laplace transform of phi t, phi s, x0 is anyways a constant initial condition. What is the phi s? Already in one of the question we revised what is phi s, Si minus a whole inverse. So let's try to first target Si minus a, and then if required we can go to the time domain if required. Okay, so what is Si minus a? Then only we can take the inverse, na. Si minus a, Si S0 0 S, correct dear? Minus a. What is the A matrix given? I'll check. Okay, minus 1 1 1 minus 1, minus 1 1 1 minus 1, minus 1 and 1 1 and minus 1. That is Si minus a. Okay, that is the Si minus a. Now, okay, sorry, if I subtract now, S minus minus 1, S plus 1, 0 minus 1, again 0 minus 1, and then lastly S plus 1. S plus 1 minus 1 minus 1 S plus 1. Okay, yeah. So what is Si minus a whole inverse? Okay, what is going to be Si minus a whole inverse? Again the same formula, adjoint. Now adjoint means change the diagonal numbers, but they are actually same. So S plus 1, S plus 1. Change the sign of the off diagonal numbers. So minus 1 will become 1. The other one also becomes 1. Divided by the determinant of Si minus a, S plus 1 whole square minus 1. Okay. So solving it further, I think, okay, I can write down this phi s as denominator 1 and 1 will get cancelled, s square plus 2s will be left. Okay, s plus 1, 1, 1, s plus 1 whole divided by s square plus 2s, s square plus 2s, this much part will be left, s square plus 2s, correct? Okay. Now, as I told you, what is x zir s in the s domain? Okay, it is phi s multiplied by x naught. What is the phi s? It is s plus 1. Now, I will divide every term by s square plus 2s, or I can take s common, s plus 2, then 1 upon s plus 2, then again 1 upon s plus 2, and the next term is again s plus 1, then further divide by s plus 2. This is phi s. This is the complete phi s multiplied by x naught, and x naught I have assumed as having the value ab. It's a good analysis question. Keep listening with me. Okay. So solving the first row and first column, what will you obtain? The first state vector in the s domain. What is the first state vector? x1s. Okay, it's going to be a into s plus 1 upon s plus 2. Okay, plus b upon s plus 2. Okay, and second row, second column will give you the second state vector, and in the s domain, the second state vector, dear, will be a upon s plus 2 plus bs plus 1 upon s plus 2. Now, let us stop in the s domain. No need to go to the time domain. No need to take the inverse Laplace transform. All that lengthy thing not required, because for t tending to infinity xt, we can apply what? We can apply the final value theorem. What is there? So, what is x1f? See further, okay, further in the question they have mentioned x1f is the final value of x1t, limit t tending to infinity x1t. Final value theorem says that this can be written as limit s tending to 0 s into x1s. Okay, limit s tending to 0 s into x1s. Now see the s tending to 0, I will solve it here. Okay, s into x1s, now you multiply s and s cancel here, s and s cancelled. Okay, so what will be left? And then put s tending to 0, so 1 by 2 into a, 1 by 2 into a. Okay, 1 by 2 into a, so that is a by 2, and next plus s. Okay, here also s multiplied. Okay, so here s and s cancelled, and then b by 2, and then what you will get? B by 2, correct now? S into this term, s and s cancelled here also. Okay, so b by 2 plus b by 2. Then x2f is given to you, t tending to infinity x2t, t tending to infinity for x2t, correct? And that is further equal to same final value theorem to be applied here also. Okay, just a second, there is some issue. No, limit of s tending to 0, I think there is some issue coming up here. I think maybe I need to restart the system, but no problem, I'll show you like this only. Now same thing, s tending to infinity, s into x2, okay, multiply s here. Okay, s cancel, then s tending to 0, a by 2, again a by 2, then multiply s here, again this s and s will cancel. Okay, b into 1 by 2, so b by 2, same result. Okay, same result, a by 2 plus b by 2. Okay, a by 2 plus b by 2. So dear, what is x? I think this slide it only is creating the problem. So dear, just a second. Yeah, so if I compare, I can say that x1f, I can compare and I can say that what is x1f, or I will directly match the option. Now both are equal, x1f and x2f are equal, and both are equal to what? A plus b by 2. Both are equal and equal to a plus b by 2. And what is mentioned here? Okay, a and b are both less than infinity, means both finite. If there are two finite numbers, some of them will also be finite. So the correct answer, x1 and x2 are equal, okay, and both of them less than infinity. Option number C. Good question, good analysis. Correct answer is C. The very correct answer is C. Okay, dear? Yeah. Okay. GATE 2018, the previous one was EE, this is IN. Okay, but you can solve this directly by the shortcut. Okay, consider the linear system x dot equal to ax. Again x dot equal to ax, no input term. Okay. X dot equal to ax, no input term. Okay, so again ZIR case. Okay guys, yeah, I think there is some issue. I need to restart, but probably this is the last question. So okay, I'll explain you this orally only. Okay, so again this is ZIR case. Again this is the ZIR case. Okay, what is the XT? XT is phi t into x naught. The options are not even asking you to multiply. Phi t into x naught. Now the shortcut you should know if you have learned about state transition matrices. About the state transition matrices, if you have learned, is the screen okay? No? Yeah, is that whenever the matrix A is a diagonal matrix, whenever the matrix A is a diagonal matrix, the state transition matrix, okay, is just also a diagonal matrix, okay, with the diagonal entries as e power lambda 1, e power lambda 2, like e power minus 1t, e power minus 2t. The state transition matrix, okay, the state transition matrix will be, okay, how much? E power minus t, e power minus 2t. Answer will be D. Okay, this is option D. Correct answer will be D. Sorry guys, some issue is happening with the system, I think, right now. But okay, I have explained you, the answer has to be D only. The correct answer has to be D. Okay, I think orally at least it is clear to you. Orally at least I have explained to you. Okay. Whenever you have a diagonal matrix, the state transition matrix will also be diagonal. Suppose the diagonal elements are A and B. So state transition matrix will have e power at, e power bt. Okay, so e power minus 1t, e power minus 2t multiplied by x naught. The x naught is one that is directly given in the question. So this one is easy for 2 marks. Straight question. Okay, straight. And whenever you study state transition matrix, that is a standard result. For diagonal matrix, what is the state transition matrix? Simple. Because many questions in other branch, in ECW also, there have been some questions around the state space model containing diagonal matrix, because diagonal matrix forms an important model, DCF. Diagonal matrix with distinct values. It forms an important form. It forms an important form. Okay, dear? All right. Okay guys, so crucial information, the new offline batches at home. Yes, if you want to excel in GATE 2026 and study with the India's best ECEE faculty team and study in front of them, okay, under the perfect supervision and also in the competitive atmosphere among hundreds of students, you can come down to Hyderabad for our offline batch. For EC, the offline batch starts July 11th. For EE, the offline batch, the next offline batch starts July 21st. The fee 65,999 is currently priced at 54,999 plus GST, and there are some special discounts which you can see. For any queries, you can contact 95156-94053 and get your doubts rectified. Okay, and yes, in case you cannot travel to Hyderabad and you have to be at your place, you are a college going student, or for some reason you have to study at your place only, so yes, you can still study by the India's best ECEE faculty team at Home Institute and enroll for our online live course. Okay, so that at least you are in live manner, one-to-one interaction with the faculty instantaneously, just like a feel of offline, and you have the same faculty, so same content, same concepts delivered to you. Okay, the fee, okay, the online live courses are available for GATE 26 and GATE 27 both, 1 year and 2 year validity. The fee is mentioned for 1 year 19,999, for 2 years 29,999 currently, and this is after discount. At the same time, okay, the OHM on this month, that is 20th of July, brings to you the online scholarship test, which can help you get huge benefits in all the online courses of home. Okay, right. So if you perform, like if you have rank 1 to 3, you can get up to 100% scholarship. For rank 4 to 10, 60% scholarship, and etc. The exam is on July 20th. Syllabus is very fundamental, mentioned in front of your screen. Okay, all right. And if you're preparing for the AE examinations, okay, that is the Transco, Discoms, Genco, etc., the new offline batches for AE starts July 15th. Okay, July 15th, right? July 15th. Okay, dear. That's it, and yeah, I'll share you the PDF. The Monday's class PDF also I have shared in my Telegram. Okay, this is the link of my Telegram. Okay, I don't think I'll be able to write down the password also. My system is hanging. Okay, you can note down the password. I'll have the password similar to the previous class. IIT GCS2, everything in small. The PDF, the password PDF for the previous class was IIT CS1, IIT G CS1, IIT Guwahati CS1. Today the password will be IIT G CS2. I think I'll write down in the comment box. Okay. Okay. The password will be IITG CS2, everything in small. I have written in the chat box. In the chat box I have written, you can take the password from there. PDF I'll share in the Telegram group. Because unfortunately I cannot take the problem again now, because as you are able to see, system is hanging. I am not able to write anything. Okay, so you can ask me maybe in the Telegram or maybe in the later session. Okay, I am not able to write anything. I'll check what is the issue. Okay, dear. So bye bye. Thank you. Now next session will be on signal and system. These were the 2 parts on control system. Similarly, I will bring 2 parts on the signal and system. Stay tuned and do not forget to subscribe the Om Institute if you have not subscribed, so that you do not miss any session. You are aware and you are notified about every session. Okay. So the next will be on signal and systems. Again, will be taken in 2 parts. Okay. Next session on signal and system. Bye bye. Thank you. Stay safe and take care of yourself.